Okay, so another open top box example. This one, they tell you how big the piece of cardboard is to start with. So that means all the way from here to here, here to here. So you just have this flat piece of cardboard. And we're going to cut squares out of the corners so that we can fold it up like this. And their question is, how big should these squares be? And so since they're squares, we know they're x by x. Whatever we cut out of one side, we're cutting out of the other side. So we're cutting these little square shapes. So say if we do like 1 by 1 or 2 by 2 inches or whatever off of each corner. Also think about like the range of that. You can't cut more than like 4 inches because you'd cut the whole thing. It's only 8 across, right? You can't take 4 inches out of each side. All right, so and we want a equation for volume. So we're saying how much do we cut out to make this box hold as much as possible or maximize the volume? Sometimes they don't explicitly say the word maximize. Sometimes they do, but that's usually that's how you know what you're trying to make your equation. Like if you're trying to maximize volume, then you want an equation for volume. All right, we know that volume, once we get the whole thing folded up, is length times width times height. But we need to translate from this flat thing to this upright diagram here. So our height, if you notice, when these flaps get folded up, the height is the same thing as x. The more we cut out of each corner, the taller those little flaps are. And so our height we're going to call x. And then we need something for width and length. So that means of the cardboard box, right? Not the 12 by 8 because it's getting smaller now that we're folding it up. That means from here to here, right across. So here's the length and here's the width of that resulting box. So notice we started out with 12 inches, but we took x off of here and x off of here. So what we're left with from here to here is 12 minus 2x. We cut a little bit out of each side. And same thing on the 8, right? We started out from 8 all the way from the whole piece of cardboard, but we cut some off here, we cut some off here. And so what we're left with is 8 minus x, or 8 minus 2x. So this is our length. And this is our width. So if we go to write down an equation for volume, it should look like length times width times height. And you could write the equation in there like that. You don't have to FOIL it together for that answer box. You can if you want to. We might have to solve here in a second anyways. But then they say find a value of x that will maximize the volume of the box. So a couple options here. We can FOIL everything together and take the derivative. Our main idea, right, is we need to take the derivative and set it equal to 0. We could put one of these in and then use product rule. Totally up to you. I'd say probably just as easy to just FOIL these two together and then we'll put the x in. So we'll just clean it up so it's easier to take the derivative first. So 12 times 8 is what, 96? FOILing. And then our inside term is minus 16x. And our outside term is minus 24x, right? 2 times 12, negative 2 times 12. So that gives us negative 40x and then plus 4x squared for our first term, negative 2x times negative 2x. And then we can distribute this x in there, which if we just want to save a line of writing, I could just do right now. So that puts an x there, makes that one squared, and makes this one to the third. So now that'll be easier to take the derivative. So 96 minus 80x plus 12x squared. And then our goal is to set that whole thing equal to 0. And then if they have a common factor, we could divide everything by something to make it smaller. Maybe at least, so we could divide everything by 6. Right, it'll still be equal to 0 on the other side. So 96 divided by 6 is 16. 80 divided by 6. Oh, 80 divided by 6 doesn't work out. Got ahead of myself. Maybe we can divide everything by 4. Obviously, you don't have to know these factors off the top of your head. I'm just checking in my calculator to see what number goes into all these. So 96 divided by 4 is 24. 80 divided by 4 is 20. And 12 divided by 4 is 3. So it probably isn't anything else that I could get into all of them. Like 3 goes into 3 and 24, but not into 20. And then it would be nice if this factored, but I'm pretty sure, and I'm just putting it in our normal order for a quadratic, I'm pretty sure that it doesn't. And if it's not going to factor, then my next best option is quadratic formula. So we could go x equals negative b is negative, and b is negative, negative 20. And then 20 squared is 400 minus 4a times c. And then all over 2a, so 2 times 3. So we have 20 plus or minus 400 minus 4 times 3 times 24. Square root of 112 all over 6. And since this is a real life problem, we can go with a decimal answer. So if I go the whole top, so square root of 112 is 10. Or 4 root 7. Plus 20. And then all divided by 2a, which is this. I get 5.097 for the one with the plus. And then we'll do the one with the minus. So 20 minus square root of 112 is like 9.4 something. And then divided by 6. So I get like 1.569. All right, so I have 2 possible answers. The biggest way to tell if any of those are even possibilities or which of them might be possibilities is go back and see what this stood for. So notice from the beginning, x was the amount that we were going to cut out of each side. So we have 2 options, 5-ish and 1.5-ish. All right, notice if I try to cut 5 out of each side, especially on this side that's 8, I go into like negative territory, 8 minus 2x. I can't cut more out of this than there is, right? I could, if I did 4 and 4, the whole thing would disappear. So the number 5 is too big to be, it doesn't mean that this whole function we wrote, it's still a solution, but it's too big for the context of our problem to be the correct answer. And so it looks like the 1.5695. And you can put it back in here to check like what volume that actually gives you. They don't ask for it in that one, I think. This was in inches, so 1.5695 inches. That one is the only one that falls in the realm of possibility. You could cut 1.5 inches out of each corner. The other one makes a box that can't exist in real life.